Okay, so this week what we want to do is we want to look at limits where we're letting our variable approach either plus infinity or minus infinity. So we're going to be looking at limits of the following form: the limit as x approaches plus infinity of some function f of x. And now this is going to equal a number L if, as x gets larger and larger and larger without limit, the values of f of x get closer and closer to the number L. So we think of this as the values of f of x get closer and closer to L as x gets farther and farther away from the origin, 0, in the positive direction. So here we have, here's 0, and now x is getting bigger and bigger. It's moving out along the x-axis, and it keeps on moving out without any limit, without any bound, and the corresponding values of f of x, they get closer and closer to the value L. So what would that say about the graph of the function f? So here's my y-axis, here's x. This is the line y equal L. And now what I know is if the limit as x approaches plus infinity of f of x is equal to L, then the graph of my function might look something like this, or it might look something like this, okay? In any case, the function, the graph of the function f of x has a horizontal asymptote along the line y equal L. Okay. And then the same thing happens if we look at a limit as x goes to minus infinity. So I have f of, I'm looking at the limit of f of x as x goes to minus infinity. This is equal to, let's say this is equal to some number m. This means that as x gets farther and farther and farther away from 0 in the negative direction, the values of f of x get closer and closer to the value m. So in that case, the graph of our function f of x might look something like this. Okay, so it has an asymptote along the line y equal m. I might mention that something else could happen, and this is not something that really comes up often in what we're doing in pre-calculus, but it does come up, and that's this. So the function might oscillate. The graph of the function might oscillate, and these amplitudes are getting smaller and smaller. So what's happening is the values of f of x are getting closer and closer to m the farther I move out along the x-axis in the negative direction away from the origin. Okay, so our graphs of the function f, they might look like this. or this, but they could do something like that also. Okay. All right, let's take a look at a typical problem. So we studied rational functions, and suppose I have a rational function that looks like this. Let's make it x squared plus 2x plus 3 divided by 4x squared plus 5x plus 6. And I want to look at the limit as x goes to plus infinity. Okay, and I want to find out, hey, does this limit exist? In other words, do the values of this rational function inside the parentheses, do they get do those values of the rational function get closer and closer to some number L as x gets bigger and bigger and bigger? Well, let's see what happens. I'm going to rewrite this. So I'm going to write this in the following form. This is the limit as x goes to plus infinity of my rational function times, and now what I'm going to do is this. I'm going to multiply this rational function by 1, but I'm going to write 1 in the following form. It's going to be a complex fraction. It's 1 divided by x squared, all divided by 1 divided by x squared. So this quantity here, this ratio, is just 1. So I haven't changed the value of the limit. Now let's do a little bit of multiplication here. So this is the limit as x goes to infinity, plus infinity, of so I'm going to multiply. This is going to be x squared plus 2x plus 3 divided by x squared, all divided by 4x squared plus 5x plus 6 divided by x squared. And this can be written in the following form. X is going to plus infinity, so it's our limit. And then I'm just going to divide here. So x squared goes into x squared one time. X squared goes into 2x, 2 over x times. And x squared goes into 3, 3 over x squared times. And then in the denominator, we have 4 plus 5 over x plus 6 over x squared. Now, what happens to the limit? So this is kind of an aside here. I'm going to put these in angular brackets. What happens to the limit of 1 over x as x goes to plus infinity? So I'm taking a very large number, a number that's getting bigger and bigger and bigger, and I'm dividing it into 1. What's happening to this? Well, it's going to go to 0, because if I take 1,000,000 and divide it into 1, I get 1,000,000th. If I take 1,000,000,000 and divide it into 1, I get 1,000,000,000th. If I take 1,000,000,000,000 and divide it into 1, I get 1,000,000,000,000th. Those numbers are getting smaller and smaller. They're positive numbers, and they're getting closer and closer to 0. And we know from our limit laws that this is going to equal the limit which is 0, okay? So now, what do we have? So this is equal to the limit as x goes to plus infinity of 1 plus 2 over x plus 3 over x squared. But what can we say about these two terms? This term is going to go to 0, and this term is going to go to 0, divided by 4 plus 5 over x plus 6 over x squared, and these two terms are going to go to 0 also as x goes to plus infinity. So I'm taking the limit as x goes to plus infinity of a numerator, which is tending to 1, divided by a denominator, which is tending to 4. So this is just going to give me 1 over 4. Let's try another one. Let's look at the limit as x goes to plus infinity again of, let's do this one, 5 times x to the 5th plus 4 times x squared plus x plus 1 divided by 5. Well, let's make it something a little bit different. Let's make it minus 7 x to the 5th plus x to the 4th plus x cubed plus 3. Okay? We want to analyze this limit. So here's what we do. We're going to do exactly the same process that we did on the previous example. So this is example 2. But the important thing here is what I'm going to do is I'm going to multiply this rational function by 1 again. But what I'm going to do is I'm going to write 1 as 1 over x to the 5th divided by 1 over x to the 5th. So how am I determining how to represent 1? What I'm doing is I'm taking the highest power of the numerator and I'm writing that as 1 over x to the 5th, and then I'm dividing it by 1 over x to the 5th by the same thing. All right, so once I do that, I get the limit as x goes to plus infinity of 5, I'm going to write it out this way, 5 times x to the 5th plus 4x squared plus x plus 1 divided by x to the 5th, all divided by minus 7 x to the 5th plus x to the 4th plus x cubed plus 3, all divided by x to the 5th. And now this is equal to the limit as x goes to plus infinity of 5 plus 4. So I'm dividing x to the 5th into x squared. That's going to give me 1 over x cubed plus the next term is going to be 1 over x to the 4th. And then the next term is 1 over x to the 5th. And all of this gets divided by minus 7 plus 1 over x plus 1 over x squared plus 3 over x to the 5th. All right, so now once again, as x goes to plus infinity, these terms all tend to 0. All of these terms are going to 0, and so my numerator is tending to 5, and my denominator is tending to minus 7. Okay. You'll remember we had the exponential function. And we saw that the graph of the exponential function looks something like this. So this is e to the x. And what did we say? When we studied the exponential function, one of the things that we noted was that the limit as x goes to minus infinity of e to the x is equal to 0. So we know that our exponential function has an asymptote. This is a horizontal asymptote along the x-axis in the negative x direction. So if I have a function, say that looks like this, let's say g of x is equal to, let's make it e to the x plus 3 times e to the 2x divided by 2e to the x plus 5 times e to the 2x. Okay? And I want to look at the limit. So this is example 3. I want to look at the limit as x goes to, let's make it as x goes to infinity of this ratio that we wrote down. Okay. Now what I could do, one of the things I can do is I can factor out an e to the 2x from the numerator. And what happens? So I'm factoring out e to the 2x, and I'm going to factor that e to the 2x out of these two terms. So when I factor it out of the 3 times e to the 2x, I'm just going to get 3. But what happens when I factor it out of e to the x? What do I get? Well, I get some quantity such that that quantity times e to the 2x is equal to e to the x. So this has to be e to the minus x here. And then I'm going to do the same thing in the denominator. All right. Well, I can cancel out these two factors. And so I'm left with e to the minus x plus 3 divided by 2e to the minus x plus 5. And now as x goes to infinity, what happens to this term? It goes to 0. And what happens to this term? It also goes to 0. So my numerator is going to tend to 3, and my denominator is going to go to 5. Okay. So that would tell me that this function g of x that we have written down, this has a horizontal asymptote. Horizontal asymptote along the line y equal 3 divided by 5. Okay. All right. Let's stop there, and we'll resume.